we want to move on to the next talk. This talk is effect of time-dependent slab age and convergence rate on slab melting in subduction zone by Yoon-Mi Kim.
Good afternoon. My name is Yoon-Mi Kim and PhD student of Seoul National University. Today, I'd like to talk about effect of time-dependent slab age and convergence rate in slab melting in subduction zones. Outline is like this. The aim of our study is how well time-dependent subduction parameters can explain the genesis of high magnesium andesite or high strontium series rocks in subduction zones. High magnesium andesite or high strontium series rocks are thought to be derived from partial melting of subducting oceanic basalt. Such slab melting requires a special subduction environment. Slab age is younger than 25 million years, and high shear stresses exist between the slab and mantle wedge, or inflow of hot metal to the corner of the mantle wedge occurring during subduction initiation or slab tearing. Previous study suggests that time-varying slab age and convergence rate can explain the genesis of high magnesium andesite in Western Aleutians. So, in order to investigate the genesis of high magnesium andesite in other subduction zones, we make two-dimensional kinematic dynamic subduction models. And with this model, we applied to East-Bonin Mariana, Eastern Japan, Kuril, Tonga, and Java-Sunda subduction zones. As a result, slab melting occurs in East-Bonin Mariana, Eastern Japan, Tonga, and Southeastern Java-Sunda subduction zones. But except for Southeastern Java-Sunda subduction zones, they are consistent with geological observation in other subduction zones. So for more detail, I will show in next slide. Yoon-Mi Kim in 2010, they suggest that time-dependent subduction parameters, including slab age and convergence rate, can explain the genesis of high magnesium andesite in Western Aleutians. Before that, slab melting is known to be occurred in young and hot subduction zones, but they suggest that time-dependent slab age and convergence rate can explain the slab melting in Western Aleutians. So with this model, we applied to the other subduction zones, East-Bonin, Mariana, Eastern Japan, Kuril, Tonga, and Java-Sunda subduction zones, including Aleutians. We make two-dimensional kinematic dynamic subduction models using recent plate reconstruction and seismic tomography model. Mantle flow and thermal structure are assumed in principle Bushnevsky approximation. Our models are made using command, and this figure shows the 2D models in each subduction zones, considering its tectonic environments. This figure shows the result of East-Bonin Mariana subduction zones. Figure A is tectonic map of East-Bonin Mariana subduction zones, and figure B and C shows the variation of slab age and convergence rate. Red line is convergence rate and black line is slab age. And figures D and E shows the depth versus temperature curves at each time step. And this line is a solidus of wet sediment, and these dot lines indicate the high and low solidity of wet basalt. So as a result, slab melting occurs from our model during 35 to 25 mA in its volume subduction zone and 40 to 20 mA in Mariana. We compare with geochemical observation in the IBM. We confirm that abundant volumetric magnetism occur in the arc in that region. Next is the result of Eastern Japan Kuriles subduction zone. In the case of Eastern Japan, slab melting is possible during 50 to 20 mA. This result is consistent with geological data. Tsuchiya and Kamisawa suggest that high strontium series rock star was derived by partial melting of the subducted ocean crust in the northeastern Japan during early Cretaceous. In the case of Kuriles subduction zones, except for 40 to 50 mA, we cannot see the slab melting in this region, and the geochemical or petrological evidence of slab melting have not been yet reported. Next is Tonga subduction zones. In the Tonga subduction zones, slab melting occurs after 45 mA from our model. Many studies have reported the occurrence of boninite in Tonga subduction zones within 3 mA. However, we cannot find the geological data related to slab melting after 3 mA. Maybe complex and large tectonic movements such as stretch retreat, recent volcanism, and leg-up opening in Lao Basin may erase the geochemical record. Last is the result of the Java-Sunda subduction zone. In the southeastern Java-Sunda slab melting had occurred in our model from 50 to 20 mA. We suggest that slab melting during this period was influenced by threat detachment. I will explain more detail in next slide. And in the case of northwestern Java-Sunda, slab melting is not possible in this region, and we cannot find the geological data related to slab melting in this region. As a evidence of slab detachment, we can see seismic gap and topography research and traditional geochemical variation between archetype and ORB type. In the southeastern Java-Sunda subduction zones, slab window underlies Java and 70 to 40 mA and was formed through subduction of the water leads. Due to slab detachment, slab dip is shallow and subducting slab is thinner, and it may influence the melting of subducting ocean crust. Generally, mantle potential temperature distribute from 1350 degree to 1450 degree. In our model, we use the upper limit of mantle potential temperature. This figure shows the comparison with previous research. Lee and Kim, they use 1350 of mantle potential temperature, and our model uses 1450. So because we use the upper limit of mantle potential temperature, so real slab melting may be more difficult than our model result. From our studies, we suggest that time-dependent slab age and convergence rate are very important subduction parameters for occurrence of slab melting. We compare steady state and time-varying thermal models in these figures. In the case of Wilson oceans, temperature profile considering time-dependent slab age and convergence rate have big variation as time goes on, different from clear subduction zones. So therefore, with steady-state subduction model, we could not explain the occurrence of slab melting in other subduction zones. So conclusion is like this. Partial melting of subducting oceanic crust is implied by the existence of high magnesium andesite or high strontium series rocks in subduction zones. So we construct a series of two-dimensional kinetic dynamic subduction models, including time-varying slab age and convergence rate for less than 50 million years. We applied to this model in Isboni, Mariana, Eastern Japan, Kuril, Tonga, and Jabasinda subduction zones. Our model results show the slab melting exists in the Isboni, Mariana, Eastern Japan, Tonga, and southeastern Jabasinda subduction zone, but the model is not expected in the Kuril and northwestern Jabasinda subduction zones. Our model result consistent with the geochemical record of our volcanism in Isboni, Mariana, Eastern Japan, Kuril, Tonga, and northwestern Jabasinda subduction zones. However, our model result is not consistent with archvolcanism in southeastern Jabasinda subduction zone. So, yeah, I think, yeah. Thank you very much.
Any comments? Question?
I could see that you imposed a rigid corner, mantle ridge corner, to the depth of say 50 kilometers. Is that right?
Pardon?
In your thermal model, you imposed a rigid corner, ridge corner, to depths of 50 kilometers.
Yeah.
Can you comment on why you picked that depth, and if you have looked at other, like if you impose the rigid corner to maybe 70 or 80 kilometer depths deeper? Have you tried?
In our model, we set up slab is kinematically described, and convection model is dynamically. So,
well, I guess I'm trying to comment on, like, if you expand the area where you impose a rigid corner, then the temperature condition of this subduction change with that too, right? Where we have surface heat flow data and attenuation, seismic attenuation observations, they sort of show that the mantle wedge corner is stagnant, like you're doing in the model, but the region that's stagnant is actually deeper than 50, maybe 70 to 80 kilometer depths. So maybe you could look at that as well. Thank you.
Thank you. Other comment? Okay, thank you very much.